So let's do a little review as we march into section 8.3, which is going to be hypothesis test for a population mean. Let's look at our symbols here. What's our symbol for a sample statistic? X bar. And its corresponding population parameter? Mu. Well done. So this is hopefully a good estimate of this. Typically you don't know what this is. Likewise down here for sample standard deviation, S and sigma. Well done. Population proportion is kind of the red-headed stepchild in this problem because it's p hat, but we don't have a Greek letter here. What is it over here? Yeah, a p with no hat. Yeah, there we go. So p. Now, we're hoping that we get good estimates of this, and we're going to use these values to test claims about population parameters. In particular, in this section, we're going to test claims about population means. So we're going to test claims about mu. I used to teach, there was a couple cases here. I used to do two different hypothesis tests. But after a while, I kind of regarded the second or the first of these cases as being kind of silly. And the first of those cases that you could teach would be a z-test. And that would assume that somehow you know what sigma is, but you don't know what the mean is, which is kind of strange. How would you know what the population standard deviation is without also being able to know what the population mean is? So that one's kind of strange. I don't teach that one anymore. We're going to assume a couple things here. Our first assumption is that we don't know what sigma is, which is a reasonable assumption. And one of two things have to be true after that. Either we have a normally distributed population, or n is greater than 30, or both. So this one, or both. Could be both, and there's nothing wrong with that. You should start to get in a little bit of a groove, starting with this chapter and moving through the rest of the course. It's going to look like this. You're going to state your null and alternative hypothesis. And I should mention kind of briefly here that there is a little bit of rhyme and reason as to how you state your null and alternative hypothesis. And I'll put this in the notes, or you can pause the video later. But keep in mind, your null and alternative hypothesis have to include the possibility of equality. This is going to go in HO, always. In HA, you'll find less than, greater than, or not equal to. And just kind of a little bonus here for you. When you're reading things, more than does not include the possibility of equality. Neither does less than. But at most means less than or equal to. And at least means greater than or equal to. So keep in mind that when you put your stuff into MyStatLab, it's not going to use these symbols. Your HO is always just going to be this. And they actually use H1. I find that annoying, but it is what it is. All right. Let's go back to this. State the null and alternative hypothesis. Decide on significance lawful alpha. That's really going to be given to you for the most part. And a lot of the rest of this is a little bit old school. The way I used to have to teach this course, you would have to compute this test statistic and find these t-values and decide if they're in the reject or fail to reject region. And you set this up so that these areas match your alpha. So in the case of a right tail test, you're going to have mu is greater than some specific value, mu naught. But we're not really going to do things that way. Step 3 is going to be input the data into, in our case, StatDisk. There's a lot of other statistical software packages available. There's SAS, there's SPSS. That's good for social sciences. There's SysStat, StatSoft, BMDP, Midas, Minitab. There's just a ton of them out there. So the nice thing about using StatDisk is you're at least getting familiar with one of them. It's pretty user-friendly. I like it. So instead of finding the critical values, you're going to input your data. And then step 4, you're going to find a p-value. So find the p-value. Once you've found your p-value, then you can make your decision. Step 5 is either to reject H0 or fail to reject H0. Under what circumstance can you use your p-value to reject H0? Yeah, so if your p-value is less than alpha, so if alpha is greater than p or p is less than alpha, then reject H0. And finally, state your conclusion in words. So for that conclusion in words, I would strongly suggest that you go back to your wording the hypothesis conclusion chart, this one right here, and look through and see, well, which one lines up with our circumstances. Okay, so we'll start out with a couple kind of warm-up problems in terms of reminding ourselves of the assumptions and a couple other little things associated with that, and then we'll do a couple problems itself. So let's see. Let's start out with, there we go. This one right here. Which of the following is not a requirement for testing a claim about a population with sigma unknown? So, okay, you've got 4 little choices there. Let's see if we can't figure out which one doesn't seem to fit or feel right. So this first one is always a requirement of our hypothesis test. So simple random sample, okay, we're good there. That one's not going to be it. The value of the population standard deviation is not known. Well, that's literally given to you right up here. It says sigma is not known. So let's cross that one out. How about the one above that? Population is normally distributed or n is greater than 30 or both. Is that a requirement for our hypothesis test? Yes. So kind of by process of elimination, we've eliminated all of these. The one that doesn't fit is that one at top. Population mean mu is equal to 1. That one doesn't belong. There's no requirement as to what your mean has to be. Nice. So not too bad to get started with. Let's move down to the next one. 12 different video games showing violence were observed. The duration times of violence were recorded with times in seconds listed below. What measurements must be satisfied to test the claim that the sample is from a population with a mean greater than 75 seconds? So what you're doing here is you're testing this claim that mu is greater than 75. But what assumptions have to be made? Check all that apply. So, okay, let's see. Does at least one of these observations have to be above or below 75? Is that a requirement here for? Well, you can look back. So you remind yourself, so there's the requirements. There's nothing that says that you have to have something above or below a certain number, in particular 75. We do have to have a normally distributed population, a simple random sample. So that one doesn't look too good. But how about the other 3? Let's see. Nicholas, how about the next one? Should that be one of the requirements that are that are true in order to do our hypothesis test here?
Yes.
Yeah, absolutely. We need that it's normally distributed somehow, either because we have a normal population or because the sample size is greater than 30, in which case we know that the sample mean has an approximate normal distribution. Awesome, thank you. Sabrina, how about the next one? The sample observations must be from a simple random sample. Should that be one of our assumptions that we meet? Yeah, absolutely. So we're good on that one. Thank you. And Ryan, how about the last one? The conditions for a binomial distribution must be satisfied. Is that one of the things we need to satisfy here?
Yeah.
It would be if we were doing a hypothesis test for a population proportion. Then you would have to have the conditions for a binomial distribution have to be satisfied. But we're doing one for a population mean, so those are the only conditions that need to be satisfied. All right, no worries. I mean, you actually learn a lot when you make a mistake, myself included. So just these two. Now testing whether or not you have a simple random sample goes a little bit beyond us. We kind of have to rely on the problem / the book to tell us that we do have a simple random sample. But let's see if the requirements are satisfied. So it's either a yes or a no. Well, let's see here. There's two requirements that we really got to worry about. One's a simple random sample. The other one's a normally distributed population, or n is greater than 30. Do we need to count here? Can you kind of eyeball that we don't have 30 observations? So what's the other possibility? What has to be true then? Yeah, has to have a normal distribution. Great. Now, we did a whole section on this. Somebody make me look good here. How can I show that something has a normal distribution? What would you do? What's that? Not that I want to call on you again, not just you're making eye contact.
Bell curve.
Ah, he has a bell curve. How can we see if it has a bell curve? What's a good way? Graph it, yeah. And what kind of graph shows us how something's distributed like that? Does everyone remember the name? Histogram, yeah, there you go. Do a histogram. Now I did put a link to the data set on D2L. If you wanted to pop that up there, you can open it up into a little Google Sheet document and then copy it over and paste it into StatDisk. So let me just do that here. Let's clear out this stuff here. Yeah, I want to clear that out. Paste it in. So there's a few things that you can do to decide if it's normally distributed. One of them which would be to do a normality assessment or a histogram. But I'm going to kind of do a catch-all thing. Let's do explore data, descriptive statistics. Column 1. The nice thing about this is we get kind of like everything in one shot. We get a histogram. What do you think? Is that looking like a normal distribution? It shouldn't take that long to think about this one. All right, no, it's definitely not a normal distribution. How about this normal quantile plot? How can you tell it's not normally distributed just by looking at the normal quantile plot? Yeah, it's not random dots, nice and evenly distributed around this line. So, yeah, this one's definitely not a normal distribution. So that allows us to go back and answer this. And in fact, if this were an SAT test, there's 3 answers that you would get rid of right away. What would those answers be that you would get rid of?
Yes.
Yep, let's get rid of these. It can't be any of those because the requirements aren't satisfied. All right. Let's see what else we got here. Nicole. How about the first one? No, because the conditions for a binomial distribution aren't satisfied? What do you think?
I don't think
I don't think so. She's not liking that one. Savannah, do you agree? You don't like that one? Do we need to satisfy the conditions for a binomial distribution here? No. This is not a test of a population proportion. If it was a test for population proportion, then we'd need to satisfy the conditions for a binomial. But it's not. No, the sample size is not greater than 30. The sample does not appear to be from a normally distributed population, and there is not enough information given to determine whether the sample is a simple random sample. That seems like it's checking all the boxes here for us, right? So that one is the right answer. You can double check it by just checking this bottom one. No, the sample size is not greater than 30. But then it goes on to say something is that there's no observations above 75 seconds. Well, that's not one of the requirements here. So that one, we'll X that one out as well. All right, are we okay with those first two there? Looking pretty good? All right. All right, thank you. Let's move on. Let's look at example C here. Now with example C, you're going to be asked to determine the p-values for your hypothesis test. Now, for the most part, a lot of this stuff is going to be given to you from StatDisk when you do your hypothesis test, but I could ask you a problem like this, in which case you're actually going to need to come up with that distribution and decide, left tail, right tail, two tail, etc. So let's take a look at the first part. The claim is that for carriers' smartphone data speeds at airports, the mean is 16. Okay, well, the mean is 16. So that's our original claim. How can I put that into words? Original claim, not in words, with symbols. So we're testing a claim about a population mean, so we should definitely use a mu here. Mu is 16. Is that going to be part of our null or alternative hypothesis?
No.
Null. All right, so that's going to be HO. So that's mu equals 16. Give yourself a second and try and determine the alternative hypothesis. Somebody gave it. Sam?
Yeah, mu doesn't.
Yeah, doesn't equal 16. Nice, nice. So, Ashley, up front. Is this going to be a left tail test, a right tail test, or a two tail test?
This is two-tailed.
Yes. Now you look at the alternative hypothesis to decide what tail test you're going to have. But basically, when you have a less than, it's going to have a left tail, not equal to, two tail, and greater than, it's going to be a right tail test. So this is going to be a two tail test. And let me draw myself a little distribution up here. Just an itty bitty one. We want to find the area in the tails, and they give us a little information here. They give us that n is 24 and t is 2.013. So, is Lizzie here? No. Oh, there you are. Sorry, you're behind my screen. I was like, I thought I remembered you here. Lizzie, if n is 24, what's our degrees of freedom?
It is 76. No.
Ooh, that's a lot. A little easier.
Never mind, 23.
Yeah. All right, so degrees of freedom is going to be 24 minus 1 or 23. Cool. And now we got to figure out, well, what's the area in the tails for these two tails? So let me draw in a little area in the tail here, and a little area in the tail here. All right, these aren't really wonderful. That's okay. Here and here. So 2.013 and negative 2.013. We need to find that orange area, the area in both tails. Now that's going to come from a t distribution. All right, so t-distribution, looking good there. Let's go to StatDisk to find out that information. You could actually find it from Google Sheets too, but for this problem, I think it's a lot easier to find it from StatDisk. Where do you think we'd go to find it from StatDisk? Analysis, good. Probability distribution, and then there it is, student t-distribution. What's our degrees of freedom? 23. And we've got a t-value, right? They told us that t was 2.013. And you get a lot of numbers here. Which number do I need? Two-tailed, right there. And you can see that if you look at the area in the right tail, if you take that area and you double it because this area and this area match, if you double that area, you're going to get the p-value, which is both areas. So the p-value is about 0.056. Value is approximately 0.056. There. Nailed it. And based on those p-values, then you can determine whether or not you're going to reject H0 or fail to reject H0. But it's good to know and understand what these p-values are. The smaller they are, the less likely that the null hypothesis is true. And at some point, usually around 5% or 1%, we say, you know what? If there's only a 1% chance or a 5% chance that the null hypothesis can be true, either we have observed something unusual or the null hypothesis is just really not true. Either way, we're going to reject it. Hopefully it's the latter case and we're not wrong, but that's where our decision is going to be made.
What did you say we're doubling for p-value?
We're just going to take the two-tailed area, but if you took a look at the area in the right tail, which is 0.02798, etc., if you double this area, you'll get exactly this value here. So what I'm saying is that this area doubled, and because they match, you can double it to get the total area. That's what's giving you, oops, sorry, thank you. This area was the 0.02798, etc., and if you doubled that, you'll get the total area in both tails. You're welcome. Let's try the next one. The claim is that the mean body temperature is mu is less than 98.6. So kind of like the last one, start out by trying to set up your null and alternative hypothesis. So here we go. That's your original claim. It's good to keep track of this. Original claim. Try and set that up as part of HO and HA. Keep in mind that the book's going to use H1. I don't know, I just like HA better because it kind of really puts alternative out there for you. Sam?
So in this instance, I would write for H null that mu is greater than or equal to
Yes.
the value, but on the homework, it only gives us.
It doesn't, yeah, exactly.
On the exam.
On the exam, I'm fine with either one.
Okay.
So Sam's point is this has to go in the alternative hypothesis that mu is less than 98.6. And for us, when we look at that, well, the opposite of this is that mu is greater than or equal to 98.6. And I'm fine with that. It's just that the book and the homework system doesn't quite see it that way. They don't use the less than or equal to or greater than or equal to. So they're just going to write mu equals 98.6. And that's fine. If they want to do it that way, I get it. So that's my stat disk or my stat lab. That's fine. On the test, I'll accept either one. Yeah, so just a nice and user-friendly there. Let's keep going. And let's see who's up next. Jackson, I've already heard from you today. So, Savannah, is this going to be a left tail, right tail, or two tail test?
It will be a left tail.
Yeah. So when your parameter is on the left side of this inequality, or equation, or not equal to, it kind of points in the direction of the tail of the test. So this is going to be a left tail test, and then of course this is two tail, and then this would be a right tail, but this is pointing in the direction of the tail of the test. So yeah, good job. So it's going to be a left tail test. Let's draw ourselves a little distribution here. And I want the area in the left tail, and that area needs to be the area to the left of negative 1.924. All right, thanks, Savannah. Mr. Snyder, how many degrees of freedom for this test?
5.
Nice. Degrees of freedom is 6 minus 1 equals 5. So let's go to the t-distribution for 5 degrees of freedom. Let's see, here we go. Oh, one more. T-distribution, 5 degrees of freedom. Our t value is negative 1 point, where was it, 924?
Yeah.
Thank you, 924. What's our p-value for this one? Yeah. No. P-value is going to be this one. Somebody said 0.072. It's got to be the area in the left tail. The area in the left tail is going to be 0.056. So just like it was in the previous problem, ironically. So our p-value is 0.056. P-value 0.056. So kind of the same as it was for the last one. Once you round it to the nearest thousandth. All right. How are we looking on that one? Feeling okay with finding p-values? Move on to actually doing the actual hypothesis test. All right, that works for me. Let's. All right, so let's flip it over to example D. Let's fix this. This comes directly from the homework, but we don't have to be as generic as it is in the homework. Park officials make predictions of times to the next eruption of Old Faithful and collect data for the errors in minutes in those predictions. The display of technology available below results from using the prediction errors to test the claim that the mean prediction error is equal to 0. So let's kind of hone in on that one. The mean prediction error is equal to 0. What would that look like in terms of an original claim? Mu equals 0. Is mu equals 0 going to be part of the null or alternative hypothesis? The null hypothesis. Good. So HO. What's the alternative have to look like? Not equal to 0. So of these four, which one looks like it fits? A. A looks like it fits. All right. So let's circle. Is it A? Yeah, A. All right, so A is the correct form of the hypothesis test. Now for this one, we're actually going to use the data. So we're not going to have some summary statistics. We're going to do the data itself. So let's open up StatDisk. And to find the data, I don't know, let's take a wild chance and go underneath data sets. And then elementary statistics. And it's data set 26 that's part of, that has the Old Faithful data. So go all the way down to data set 26. So one more time, it's data sets, 14th edition, Old Faithful, and there's your data. Except we want data for the predicted error, which is going to be in column 5. So that's where we're going to get our data. Sam? Maybe Cosmo, can you share your screen with Sam?
Oh,
you got your tablet? Okay.
I had it up.
I couldn't see it.
I'm sorry.
All right, no worries, no worries.
Showing data in your lecture. Looking right at it.
Great answer. That's like this extra credit worthy of an answer. All right. So if we're going to do a hypothesis test, then let's go down here to hypothesis testing. Which one do I want to choose? Yeah, you've only got one sample, so it has to be either proportion, mean, or standard deviation. Standard deviation is coming up next. Proportion we've already done. Is our alternative hypothesis set up the right way? Yeah. Actually, before we get there, we're going to click Use Data, because we actually have the raw data. Now, a lot of times you feed in summary statistics. That is, they'll tell you what the mean and standard deviation was. But this time we actually have the raw data. So click that. Our alternative hypothesis is still correct. Our significance level. What significance level are we going to use here? 0.05. What's the symbol for that significance level? Alpha. Good. So right there, alpha is 0.05. Okay. Do we know, let's see, what's our claimed mean? What's our, 0. That claimed mean is always going to come from H naught. The null hypothesis. That's your mu naught if you wanted to kind of line this up with our handout from earlier. So there's mu naught. Claimed mean is 0. Do we know the population standard deviation? No. Think what that would mean. That implies that somehow we don't know what the population mean is, which is why we're testing it, but somehow we do know the standard deviation. That just wouldn't make sense. So you're never really going to fill this in when you're using this test. The sample that contains your data, or the column that contains your data, is prediction errors, 0 minutes, and bam. There you go. So let's run through a few steps here. Try and work through our analysis. Step 1 is to state the null and alternative hypothesis. Step 2 is to decide on alpha. Step 3, input the data / summary statistics. Now in this case, we actually input the raw data itself. What's step 4? Does anyone remember what step 4 is? Yeah, to find the p-value. P-value in our case was 0.0000, right? Bunch of blanks. Step 5, you got to decide if you accept H naught, or if you fail to reject H naught, or reject H naught. So let me pick on somebody here for step 5. And let's see. Alex, have I picked on you today? I don't think I have.
Reject H naught.
Yeah, reject H naught. P is less than alpha. And if you ever see some math text, you'll see a little triangle of dots like this sometimes? That means therefore. Therefore, reject H naught. All right, great. So now we got to state our conclusion in words. Let's be careful about stating our conclusion in words. I don't want you to use words like parameter or null hypothesis in your conclusion. Your conclusion should be written in a nice, friendly way that can be read or understood by just about anybody. So that's where you're going to get this nice little form out here for us. Let's see, where is it? Wording the conclusions. No, that's Wordle. Wording the conclusions. Try a better one. There we go. Now let's pick this one. All right. So you got 4 possibilities here. Try and decide which one of these you're going to use, A, B, C, or D. I'm going to give you a second to look at that one. Look back at your original claim. In fact, we can look back at our original claim together. That much will do. My bad for not kind of highlighting that as we started out. But this was our original claim right here. So original claim is that much. Mu equals 0 was our original claim. So with that, let me see here. Ian, and back. Which one of these do you think we're going to use? You can just do A, B, C, or D. C? Let's think here. So our original claim contained the condition of equality, right?
Yes.
So that means which way do we branch out of this box? Down and to the right or straight to the right? Straight to the right. Did we reject H naught?
Yes.
So which one are we going to conclude then? A. There you go. So there's how you start this. There's sufficient evidence to warrant rejection of the claim, and then just fill in the blank with the original claim. What does the original claim mean in words? So, all right, let's do that. There is sufficient evidence to reject the claim that the mean prediction error for Old Faithful eruption times is 0. Notice I didn't use any symbols. I don't want to see less than, greater than, or equal to symbols in this conclusion. Nicole?
So in the answer where it says identify the test statistic versus -7.17.
Sure.
We're coming from.
All right, so when the book does these things for you in homework, it kind of randomly generates some of this data. So these values aren't always going to match what we get in class. In this particular case, I trust our values because they're coming from the exact data set itself. But let's actually get those values for us in this particular case. So good question here. Let's go back. It says identify the test statistic. Okay, well, let's see. For analysis, you can reclaim. Okay, test statistic. There you go. -8.72. That would be our test statistic for this particular problem. So -8.72. And the p-value, I think, was still 0. So that didn't change even though the test statistic did. So good question. Now, the reason to use a test statistic is because in the old days, we used to have to decide. We had to find these values in red, which was a whole chore in and of itself. The values to the left of this or to the right of this represent the rejection region. And if your test statistic falls in the rejection region, that means it's really unlikely that the null hypothesis could be true for your data. So either you got lucky and got some unusual data, or the null hypothesis is false. And when you get a test statistic out here, we generally say, yeah, no, I think the null hypothesis is false. And we're seeing that with a really low p-value. I mean, our p-value is essentially 0. So it's very unlikely that we could get this data unless the null hypothesis was false. So we can feel pretty good about rejecting H0 in this case. All right, great question. Let's see. How about if we finish this up with a confidence interval, just for giggles, just to make sure that we understand what the confidence interval is saying compared to what our hypothesis test is saying. Now, when I do a confidence interval for this, do you think my confidence interval is going to contain 0 or not contain 0? Keep in mind we rejected this hypothesis. It shouldn't contain it, right? Because our confidence interval is really saying, well, where we think the parameter is. And if the parameter is actually in there, we shouldn't be rejecting H0. So let's take a look at the confidence interval and see that those things match each other like we expect them to. So I'll go to analysis, this time confidence intervals, mean, one sample. Let's use data, might as well. 95% confidence level for column 5, prediction error. And there you go. Actually, I think this was actually part of our output in the previous screen there, so I probably did a little bit more work than I needed to. But our confidence interval doesn't contain 0. We can be 95% confident that the true mean prediction error is between negative 4.03 and 2.54 minutes. Basically, get there a little bit early, otherwise you're probably going to miss it if you're just going by their predictions, is what you're saying there. The big thing to notice is that that interval doesn't contain 0. So good on that one. All right, let me write that down. This is just kind of like a bonus. I'm not sure I don't think I'll always ask you to do both of these at the same time. And like we mentioned earlier, usually these things should match. We can be 95% confident that the true mean prediction error for Old Faithful eruptions is between negative 4.03 and negative 2.54 minutes. So the message is get there early. Now on the exams, when you're stating your conclusion about confidence intervals, a couple things that I'd like to see. I want to see the percentage of, or your level of confidence, but don't use the word probability here, because the word probability is wrong. And I want to see the word true. True, whatever it is, true mean, true proportion, true standard deviation, etc. So those are some of the things I'd like to see as part of your work there. Comments or thoughts on that last one? Hopefully that's wrapping it up together pretty good. And let's put this one in the books.